Welcome back to the EMWorks video series. How to optimize the air gap for an arcing horn and high voltage lines. The arcing horn is a genius solution to protect high voltage transmission lines and transformers during a lightning strike, a sudden load variation, or any other faulty condition. However, the arcing phenomenon is heavily dependent on the sizing of the air gap between the high voltage line and the ground. In this video, we will show you, step by step, how to use the EMWorks virtual prototyping software, EMS, to simulate and optimize your air gap for a safe flashover, faster and at a lower cost. Since EMS is an add-in to SolidWorks, the #1 3D CAD software, the creation and modification of the model is as easy as a pie. Therefore, we skip the geometry creation part and dive straight into EMS. To achieve our goal, the parametrization feature of EMS is used. To add a new study, right-click on the project name and choose Electrostatic. In the General Properties tab, check Parameterization. Check also Compare Fields to Breakdown Level. No need to check the other tabs. The default is adequate for this application. Click OK. A new parametric study is added to the EMS Manager tree. Let's apply the material for each body. Right-click on 30NF251 part to apply porcelain. Similarly, you can follow the same procedure to apply material to all other parts. Since we applied materials in a previous study, just drag and drop materials from Study 2 to materials in Study 3. Let's apply the necessary load restraint. Right-click on Load Restraint and choose Fixed Voltage. Select the ground parts, as shown. Take the default 0 volts. Click OK. Again, right-click on Load Restraint and choose Fixed Voltage. Select the high voltage part, as shown. Type 10,000 in the voltage field. Click OK. Click back on the SolidWorks Feature Manager design tree. Define a global variable D1 that represents the length of the air gap. If you do not know how to create global variables in SolidWorks, please refer to the SolidWorks help. Click again on the EMS Manager tab. Right-click on the project name at the root of the EMS Manager tree and choose Parameters. Import the global variables from SolidWorks and check OK. Right-click on Design Scenarios and choose Edit Definition. For parameter type, choose Range with steps for D1. Enter 10, 15 and 2.5 for the minimum, maximum, and step, respectively. Check Simulation Variables. Choose Load Restraint. Choose Fixed Voltage 2. Click Add. Enter 10,000, 60,000, and 50,000 for the minimum, maximum, and step, respectively. Click on Generate Scenarios. 6 scenarios are thus created. Click OK. All the pre-processing is now complete and we are ready to run the parametric study. Right-click on the study name and choose Run. Of course, it would take some time to run it. Let's instead examine an existing study that was run previously. To show the fringe plot of the electric field, just click on the electric field icon. The magnitude of the electric field is color-coded where the red color is the maximum and the blue color is the minimum, as shown on the legend on the right side of the plot. As expected, the electric field is concentrated in the air gap. To better visualize the electric field, right-click on the icon and choose Edit. Check the Show Plot Only on selected entities. Choose the air gap part. Right-click in the graphic area and choose Zoom to fit. Check Plot All Scenarios. Click OK. All the scenario plots are added to the electric field folder. Double-click on the plots one by one and note the minimum and maximum values. Clearly, scenarios 4 and 5 are adequate to produce an arc in the air gap. In scenarios 4 and 5, the electric field exceeds the air breakdown of 3 million volts per meter in the entire air gap. To check the values of the air gap size and the voltage that correspond to scenarios 4 and 5, right-click on Design Scenarios and Edit. Scenario 4 corresponds to an air gap size of 10 mm and a voltage of 60,000 volts. Scenario 5 corresponds to an air gap size of 12.5 mm and a voltage of 60,000 volts. This will cause the ionization of the air gap, which, in turn will cause corona, leading to an arc between the high voltage line and the ground. The arc will act like a conductor connecting the high voltage to the ground. Consequently, the flashover will go from the high voltage line to the ground via the arc. The bushing insulator is thus saved. Another way to examine the results is to plot the safety factor. Borrowing from structural engineering, the safety factor was coined by EMS. It is the ratio of the electric field strength in a region to the dielectric breakdown value in that same region. In other words, if the safety factor is less than 1, there is no breakdown, hence, no corona in that region. Let's plot the safety factor in the air gap for all scenarios. Right-click on the Safety Factor folder. Choose 3D Fringe Plot. Check the Show Plot Only on selected entities. Choose the air gap part. Right-click in the graphic area and choose Zoom to fit. Check Plot All Scenarios. Click OK. Double-click on the safety factor for each scenario. Again, scenarios 4 and 5 are adequate to produce an arc in the air gap. In scenarios 4 and 5, the safety factor exceeds 1 in the entire air gap. It is the same conclusion as the one reached via the electric field plots. The safety factor is more convenient than the electric field. Instead of memorizing the dielectric breakdown of a certain material, just remember that a safety factor less than 1 means no breakdown, and vice versa. One last check to do. We must make sure that in scenarios 4 and 5 the bushing insulator is safe. Right-click on the safety factor folder. Choose 3D fringe plot. Choose scenario 4. Check the show plot only on selected entities. Choose the bushing insulator part. Clearly the safety factor is well below 1. The bushing insulator is thus safe. Let's do the same for scenario 5. Again, for scenario 5, the bushing insulator is safe. We can, therefore, confirm that using the parametrization feature, you can easily size the air gap that will assure the formation of an arc. At the same time, it assures the safety of the bushing insulator. A tool like EMS is indispensable to design and optimize arcing horns and other insulating systems. You cannot guess it. You must simulate it. Thank you for watching. Bye now until the next video. Stay tuned.